In this activity, you will be analyzing spectrometer data for various light sources. A spectrometer is an instrument which helps us resolve the different wavelengths or frequencies that emanate from a light source. Now we have a tiny spectrometer in the lab. We call it the USB spectrometer because it's just a small box that you can hold in the palm of your hand, and all you need to do is to connect a wire to the computer via an USB port and another optic cable from the light source to the spectrometer. So that's the schematic of the spectrometer. The light enters in, and using a series of mirrors and gratings, there is a dispersion of the light, and there is an electronic circuit which basically helps us plot the spectrum, and there is a calibration which allows us to directly calculate the wavelength. So this is the kind of data that you will get when you perform a scan of the spectrometer, and this data will be provided to you in an Excel sheet. So this is intensity versus wavelength in nanometers. So there are different sources here. You have LEDs, you have a tube light, you have a halogen lamp, you have the spectrum from the sun, you have a mobile, you have different lasers and so on. So the first part of the experiment is you will have to plot each of these spectrum, and you will have to write a short note about what is the kind of spectrum that you are seeing, and you have to describe the features of the spectrum. It's very easy to simply do some research on it online and write a couple of paragraphs, not more than that. For each of the spectrum. For example, take the spectrum of the sunlight here and explain why you see those dips here, and what does the width here means, and so on. And you can see some of these sources are broad. The line shape is broad. Some of them are extremely narrow, obviously like a laser source. So the first part of this experiment is you'll have to plot them and write a short explanatory note about what the spectrum is and what are the main features in it. In the second part, you take some of them, like what I've shown here, the LEDs, the laser diodes, the sodium lamp, and so on. The ones which are nicely peaked, which give you a nice peak, which is either broad or narrow, and you will have to find what is known as the full width at half maximum. So this is the lambda center. We'll call this the peak here. The intensity peak corresponds to lambda naught. That's the we'll define that as the resonance wavelength, and this intensity is, let's say, 6500 units, some arbitrary unit, 6500. Half of that, somewhere around here. So at half intensity, you will have to find out the width of the spectral line, this distance, full width at half maximum. That's defined as the width of the spectral line. That's an arbitrary definition, and this is some delta lambda. So you will have to calculate the delta lambda for these sources using the data given to you. You will need a computer to plot this. So you can't. There are too many data points. You cannot do it on a graph sheet. Now, using this delta lambda, you will calculate the temporal coherence of those light sources. Now, the temporal coherence of the light source is basically a measure of how monochromatic a source is. So, given a wavelength lambda that comes from the light source and a wavelength lambda plus delta lambda, so some increment or some deviation from that lambda. So there are two wavelengths that come from the same light source, lambda and lambda plus delta lambda. What is the largest distance or the largest path difference over which interference is possible between lambda and lambda plus delta lambda? That is known as the coherence length, and from that you can define a corresponding coherence time. So you have a delta lambda, which is the width of this, the full width at half maximum. There's a delta lambda here. So for that delta lambda, there's a corresponding delta nu. There's a corresponding difference in frequency, and we can invert that 1 by delta nu and call it a coherence time. So if I multiply this coherence time tau naught with the speed of light, then I can define a coherence length, and I can rewrite this as lambda squared by delta lambda. So the coherence length lambda squared by delta lambda is a measure of the largest path difference for which interference is possible. So if I given a wavelength lambda and another wavelength lambda plus delta lambda, for any wavelengths within this range, you can define the source as monochromatic. That is, you can have interference patterns between lambda and lambda plus delta lambda. If the wavelength deviates beyond the lambda plus delta lambda, then interference is not possible, and we will say that the source is for that region the source is not monochromatic. Interference is, I mean, there is no coherence. There is no coherence between the phases of the light wave at different points along the direction of propagation. So you can measure the coherence length, or it's a measure of how monochromatic a source is, and that is defined by lambda squared by delta lambda. So lambda is basically this peak line here, that is the resonance wavelength, that is lambda, and you measure delta lambda. You look at the intensity and you measure the delta lambda at half the intensity, the width at half the intensity. So lambda squared by delta lambda will give you the coherence length, or a measure of how coherent a source is. So for example, if you take a laser source, you can have coherent lengths of few meters, even more than that, tens of meters, 5 meters, 10 meters, and so on. So you can, so given a laser source, you can the laser source is so coherent in terms of you can define the phase of the wave so clearly that the wave can create an interference pattern over that distance. Whereas if you take sunlight, it will be the coherence length will be so small that you can see interference pattern only over the thickness of a soap bubble or a soap film. That's because sunlight is not a monochromatic source, and it doesn't have too much of coherence. So what you will measure from this lambda squared by delta lambda is the coherence length, or the largest path difference over which you can over which interference is possible from the source, and it tells you how monochromatic a source is. So you will measure this full width at half maximum. So this is shown here. The center of this peak is lambda naught. That's the lambda or lambda naught. That's the resonance wavelength. And from this peak intensity, find out half the intensity. At this half intensity, find out this delta lambda. That's from that delta lambda. Find from lambda squared by delta lambda, calculate the coherence length. So you will have to do two activities: plot the spectrum for each data source, calculate the full width at half maximum, and from that calculate the temporal coherence of each source and draw inferences from your result, and write a short note explaining the nature of each spectrum. Not a couple of paragraphs, not more. So this temporal coherence bit you have to do only for certain light sources, like shown here. For example, the LEDs, the red, green, blue LEDs, the laser sources, sodium, the mobile, the mobile source, then the green and the red laser diodes. Only for this. Then there are additional sources like halogen lamp, tube light. These are obviously not monochromatic sources. You don't need to calculate temporal coherence for this. But you can just along with the others, you can also explain why you see this, why there are dips here, and so on. Just write a short explanatory note. That's the experiment.